So, hello everyone. Today we will be talking about the differential equations and the way differential equations are solved. So, this is the lecture 4 in our series. So, before this, we had talked about some fundamental concepts of calculus and their intuitive meanings, followed by certain expansions. And now we are trying to deal with the differential equations. And just to focus on the word differential indicates that there is some form of derivative in the equations that we'll attempt to write. And by doing so, we'll try to formulate some equations and thereby propose certain methods to solve them. And that is all about this module, because here we are trying to find out solutions to problems that involve derivatives as well as their functions. So our differential equation has many forms, but of them we are trying to do the first order differential ones. So first order differential equations, and that's the topic for today's discussion, and some of the ways that in which they can be solved. Okay. So without further ado, let's go into the way in which a differential equation is expressed in the first place. So any first order differential equation, the way that we're trying to propose it, can be written as dy by dx, which is the derivative of y with respect to x, is a function of x and y, where x is the independent variable and y is the dependent variable. Okay. So we see that it involves a derivative, as we have seen so far, where dy by dx indicates the slope of the curve, and the curve is y. We'll talk about more about the curves and what does y equals to fx really represent in a short time. So what we see over here, that this compact form is a differential equation which leads the solution y equals to fx. That's the standard form that we have seen so far, and it is a solution of this differential equation. So this comes from the differential equation that we see over here. So once we have achieved this workflow, we need certain methods to ensure that we understand what it physically means. So the physical interpretation of the differential equation, as we see over here. So then we check certain things and we try to figure out what this really means. So if y equals to fx is a curve, so we are trying to propose that this is a curve, so dy dx is essentially the slope of the tangent at a certain point in the curve. So this is what the explanation of y equals to fx really means, that it is the slope of the curve at that particular point. Okay. So here y equals to fx, as we will shortly see over here, is, and we saw it just a while before, this is also the solution of the curve of the differential equation, does not denote just one curve, but a family of curves. Okay, so family or a collection or a cluster of curves which have similar properties except for a certain parameter which kind of changes one of their properties, but really most of its characteristics remains the same. So y equals to fx does not really denote one curve, but in fact a family of curves. Okay, so this is what we're trying to understand from when we say that if it's y equals to fx and that is obtained from a differential equation, in that case it describes a family of curves rather than a single curve. Okay, so at this point it's good to understand that these differential equations also hold good when these differential equations yield solutions which look the form if y equals to fx. Then we should clearly have this in mind before jumping in to solving it, or even using differential forms, or even point-wise forms where you insert boundary conditions to get certain values of the equation, or get the equation in its compact form. Okay, So let's check what we mean by a family of curves. Okay, so let an equation x squared plus y squared equals to c, and then this equation this equation represents a family of circles of radius root c, and it is centered about the point 0 comma 0, which is essentially the origin in a rectangular orthogonal coordinate system. So we see that the radius is root c, and the only parameter that can be used to change this value of the radius of the circle is through the manipulation of this parameter, which is c. So c can have any value from c1, c2, and that is plotted over here as we see in a orthogonal coordinate system. And we start drawing curves. And the first one is c1, and then the radius is root c1. The other is c2, the radius is root c2. From these curves, we see that all the properties of the curves are same. It's just that we are simply changing the radius, and that's the only thing that is changing. Other than that, the nature of the curves is exactly the same, and there is really no difference from it to the other. So this is one aspect of the differential equation, that it helps to predict a family of curves. So once we are done with this, I would suggest you take a break in a while in this point and kind of go through what we have done so far before we proceed on to the order and degree of a differential equation, which is a fundamental concept, because order and degree of a differential equation really dictates how you're going to approach the problem and what your solution strategy really is. Okay, so the definition of order says that it is the order of the highest, and I highlight the word highest because it is really easy to get into confusion when doing big problems. So it's the order of the highest differential coefficient present in the differential equation that we have at hand right there. So we need to find out what is the highest derivative that has been taken into account in the problem, and that is essentially the order of the differential equation. So right now we're not looking at exponents. We'll look at exponents in the next part, but the one that I have highlighted over here really shows the three terms over here. One of them has a second derivative, the second one has a first derivative, the third one has no derivative at all. So the one which has the second derivative is the one which governs the equation. So that is the order, and for this problem, this is second order differential equation. So we see over here this is a second order term, and this clearly is the definition of order when we need it. So this is the first part, which is order, and then we talk about degree. So the degree of a differential equation is equally important when you're solving for problems, and getting these things in your fingertips is really necessary. So I would suggest you go through the definitions as many times as you want, repeatedly, so that this thing, it becomes sort of a muscle memory instead of you going back and forth to the definition and then solving your problem. So when you talk about degree, it's the degree of the highest derivative that is there in the differential equation. So once you have the highest derivative, and then you remove the radical signs and other things such as the fractions, you remove all of them, and then you choose the highest derivative, and the degree which corresponds to the highest derivative is the one which is the final degree of the differential equation, because that is the one which drives the problem. That is the one which kind of governs what solution strategy you're going to use for the rest of the problem, and that is the one which is the deciding factor. So for an equation which looks like d to y by dx2 whole square plus 2 dy by dx to the power 4 plus 3y is equal to 0, in this equation we see over here that the first term corresponds to the highest derivative that is there in the equation, and the power corresponding to this degree, this particular derivative is 2. So hence the degree of this differential equation degree is 2. Okay, so it's a pretty straightforward understanding what we're trying to do, but then this needs to be there at the back of your mind when you are solving problems, because this is essential when choosing what kind of solution strategy is going to be implemented, which method of differential equation is going to be implemented. Okay, so this is all about degree and order of a differential equation. So now that we have reached at this point, we're taking a leap forward, and you can pause this video at any time to check what we have done so far, and then we are going forward into a next segment in a while, in which we really attempt to solve the problems and then ensure that we are well equipped with all the tools that we have when we're trying to solve for these kind of problems so far. This isn't nothing new. It's just that we're trying to recap everything that we have learned, that going forward we don't need to emphasize much on these things and straightly go ahead into the problems. Okay, so when we talk about these things, let's start with one fundamental aspect, which is differential equations of the first order, and that's the most simplest type that can happen, and the first degree. Okay, so we're trying to do differential equations of the most simplest version, where we have order is equal to 1, degree is equal to 1, and some of the solution strategies that will be used for this thing. So we say that if a differential equation can be written in the following form. So we propose a form that needs to be satisfied. If we can manage to write a differential equation in this form, fy dy is equal to phi x dx, where fy and phi x are two different functions, each depending on their corresponding parameters. For example, fy depends on the dependent value, which is y, and phi x depends on the independent parameter, which is x. We say that variables can be separated, and this form of solution, this method which we will implement to solve for differential equations, is essentially known as a separation of variables method. And all of this should stick to the condition that you take all your y components onto the left hand side. As you see over here, the left hand side of the above equation says that fy and dy, because dy is the differential term, and on the right hand side we have phi x dx, which means on the right hand side we have two terms. So if we want to do this, we take all the y components on the left hand side and the x components on the right hand side, okay, as I've written over here on the right hand side, and then try to do some integration as we have known so far, and then get our corresponding results. Okay, another way to write that would be, and this is a more general form, dy by dx is equal to fx comma y, if this function that we have dealt so far is of the form phi 1x by phi 2y. So we have seen that a differential equation looks like this. Now if the function on the right hand side takes the form phi 1x divided by phi 2y, in that case this generally holds. So phi 2y, if we cross multiply it on both sides, so phi 2y dy is equal to phi 1x dx, and then we take an integration on both sides. In general, if you don't have any other condition for x and y, this is an indefinite form, and this will have a constant plus c attached to it, as you will see in the following examples that we will solve over here. Okay, so at this point it is wise to pause the video and then check what are the conditions that we have in which and how we should arrange the variables to make sure that we can use the separation of variables method properly. But nothing goes without solving examples, and that gives a better idea of what we are trying to say over here, right? So example 1, we'll try to approach a problem and then see how it is solved. So solve the differential equation. Solve the differential equation over here. And then this will mostly be an indefinite form. We will do some definite forms later, but then This is using the separation of variables method. Okay. And then we write the equation uh, accordingly. So we have y x to the power 2 plus y dy. So dy has a factor of y x squared plus y plus x y squared plus x dx, and that is equal to 0. We see that the term which is attached to dy is a mixed term containing x and y, and the term attached to dy is again a term which is a mixed combination of x and y, which is not purely fx or phi y or something like that, right? So first of all, we need to ensure that these terms are purely written in terms of y or purely written in terms of x. Okay, so I repeat it again. If you want to use a separation of variables method, make sure that the terms on the left are completely in form of y with the dy attached to it, and the term on the right are terms which completely depend on x. So as the first strategy, we are dividing both sides by dx so that we get the differential form, as I said in the second definition. And then you have y dy divided by y squared plus 1. So we take y common from the first term and x common from the second term, and that is equal to minus x divided by x squared plus 1. Okay. And then dx, because we also need to integrate that accordingly. So these are the two terms over there. There you go. So these are the two terms that we have, and now clearly it can be seen that on the left hand side you have a pure term in fy and dy, and on the right you have a term which is phi x and dx. Okay, so it can be integrated properly. I leave this integration to you as an exercise, but this is pretty intuitive. And then we get a term involving a logarithmic expression and a constant, of course, because we are doing an indefinite integral, as I've been telling you previously. We have been doing an indefinite integral, so we will get a constant after the integration, and that is attached to the logarithmic function, right? So in order to make sure that we have a compact expression, we need to take the right hand side to the left hand side, and then add the two logarithmic terms, thereby making sure that you have a complete expression. Okay, and as we know that log of ab is equal to log a plus log b, that's a pretty basic operation of logarithms. So we multiply the two terms over here, and then we are good to go with the final value or the final expression that we obtained from the differential equation, right? So if the log term is a constant, the term within the log term is also a constant. That's pretty obvious. Hence, we have x squared plus 1 multiplied with y squared plus 1 is equal to a constant, which is c. And that's the solution for your first differential equation using separation of variables. So you just saw that how separation of variables technique can be used to approach the problems. And this is a indefinite setup in which you have a constant c. But in some cases, you do need to calculate the value of the c, as you will see in the second question. And once again, I leave up to you the exercise that I've just marked. You can do the integration. It's pretty easy to see how the integration happens, but it's pretty trivial, and you don't need much, work to work it out. Okay. Let's go to the second problem now. So solve the differential equation, and now we say that we are using the separation of variables method. We use the acronym SOV. Okay, so we write the equation now, the differential equation that will be used, in which you have e to the power y plus 1 multiplied with cosine of x dx plus e to the power y sine x dx dy, and that is equal to 0. Okay, and now there is a condition, a constraint which is given. It says that y of pi by 3 is equal to 0, right? So we say that when x obtains the value of pi by 3, the function y takes in the value of pi by 3 and results a number which is null. Okay, so this is the complete statement or the complete form of the problem. So once we have reached to this point, now we have all the tools that are necessary to formulate the problem in a certain way and make sure we use the separation of variables accurately to get it. So one of the first observations that you see over here is the cosine x and the sine x can be brought together, and the ey and the ey plus 1 can be brought together. So that will make sure that you have a homogeneous function in fx, or a function which only has x terms and a function which only has y terms. Okay, so cos x by sine x dx is a term which only involves the x terms, and e to the power y by e to the power y plus 1 dy are terms which only contain the y. So these arrows marked over here make sure that you understand how the switches happen. Okay, we just need to take it from that side and do an integration over here. It's pretty simple. Integration over here is again very intuitive. You can use you can try to do that, but it's a pretty simple integration over here, where you have ln of sine x, and then the second expression is ln of e to the power y plus 1. Subject to the constraint that you obtain a value of c on your right hand side by inserting the above condition of y. It takes in pi by 3 and gives in 0. Okay, so ln of sine x plus ln of e to the power y plus 1 is equal to log of c. That is the first form which is there. And this expression can again be combined together using logarithmic properties. So we obtain the expression as you see over here. So the final form of the differential equation can be written as the sine x multiplied with e to the power y plus 1 is a constant. Okay, so this is halfway through the problem. You have obtained an expression, but then you need to satisfy some other conditions as well in order to find out what is the value of c, because this is a definite problem, definite form of the problem. Also, like you can also see it as a definite integral, because the integration contains a sign which will be replaced soon. Okay, so now we use the boundary or the given condition in which you have the definite form over here. So if you have x equals to pi by 3 and then y is equal to 0, okay, so y is equal to 0 over here, right, plus 1. So that is essentially equal to c, and we shall soon see that c is equal to square root of 3, because sine pi by 3 is 60, sine 60 is root 3 by 2, and e to the power 0 plus 1 is root 3 by it's 2. Okay, so here's the final form of the expression that you have. You already had the left hand side. The right hand side is a simple substitution. So there you have the two equations that you need for the problem, the two equations that are really important for your understanding, the two problems that we did just now. And as a third problem, we will demonstrate a technique which employs the separation of variables pretty subtly and pretty intelligently. Okay, this is a very standard technique again, but then this will allow us to appreciate how the variables are used and how the whole thing goes in. Okay, so into our understanding, of course. So x to the power 4 dy dx plus x cubed y is equal to minus sec xy, right? So as you see over here on the right, you have a combination of the two functions, right, x and y. So you've multiplied x with y. Essentially what we did was we took the independent variable, which is x, and then the dependent variable, which is y. So that is a combined function. And now we will adopt a strategy to ensure that we can tackle this problem as well using the separation of variables approach. So we start with the solution. You can try the solution before going through this, but let's just start with the solution. Okay, so x to the power 4 dy dx plus x cubed y is equal to minus second xy. Okay, the first thing that you should see over here is that x cubed can be taken common from these two terms. So we take the x cubed common over here. and then see what else can be done when we have to use the separation of variables. Okay, so I've highlighted these two expressions over here, the two terms, and then we take x cube as common and then write the rest one as x dy by dx plus y is equal to minus second xy. Okay, so at this point we need to just understand that we need a variable which can do the function of xy, right? So we replace v is equal to xy. So v is the replacement for the right hand side's argument, which is xy of the second function. So v is equal to xy, and then we take a derivative of v with respect to the independent variable, which is x. Okay, so dv dx is equal to x dy by dx plus y, and you can see that this is pretty similar to the one which is above this line, right? So it is pretty similar to the one above this line, and we can see that we have actually made a possible replacement for the term in brackets just after x cube. Okay, so we can replace the term after x cube with dv dx, right? So we can do that, and that will help us to arrive at a solution which looks somewhat familiar to the so that we can apply the separation of variables method, right? Okay, so just take a moment to appreciate that these are certain techniques which can be done and pretty intelligently to make sure that we understand separation of variables properly. Okay, so x cube is multiplied with dv dx, which is the derivative of v, the replacement function with respect to the independent variable, and that is equal to minus second of v, right? So we no longer have to deal with xy, we just use x and v as the base variables for the separation of variables method, right? So now the problem is pretty straightforward, where we have dv by dx is equal to minus dx by x cube. So using the method, and then what we do is we do an integration over there, because this is also an indefinite problem. We don't have any conditions as such which is given, so we'll just make sure that we replace the values accordingly, and then kind of do the integration, which is pretty straightforward, pretty trivial, and can be done really easily. Okay, so an integration of this one, the one that is marked over here, is sine v is equal to 1 by 2x square from the second term over there. So it's equal to 1 by 2x square and then plus a constant c. Okay, so now that we have obtained this expression, it is pretty safe to replace the value of v from the replacement that we did previously. So now we replace v with xy, because that is where we'll get the final result. Okay, v is replaced with xy. So once we have that, we can obtain the final form, which is sine of xy is equal to 1 by 2x square plus the constant. So this is the family of curves, or the final solution of the differential equation. Okay, so I hope you've learned something from this module. We will talk about other methods. We'll talk about some other things that we have in store. For example, we will talk about other solving techniques in the following lecture. Followed by that, there'll be a discussion on some more problems of differential equations, and that will wrap up this module, and then we will switch on to the next module where we will discuss concepts which depend on this particular understanding. So thank you for your time. I hope you have liked the video so far.